Okay, in our second day of probability here, we're going to be talking about conditional probability. So conditional probability is when you have a condition that may limit the sample space, meaning the sample space is everything that could happen. So when we limit the sample space, we say something has happened that is going to limit what we are actually finding the probability, the total from. So the first I'm going to start off with here is how to find the probability of two independent events. If A and B are independent, so I'm looking right here. If A and B are independent, the probability of A and B happening is simply the probability of A times the probability of B happening. So the word and will generally mean multiplication in probability. In fact, I'm going to put that here too. The word and usually signals that we're going to be, that we are usually going to be multiplying. And we've seen already that when you are finding the probability of A or B happening, then in general, you will add the probabilities. So what we're going to start off with here in a conditional probability is talking about what the notation is for that. The probability of B, given that A has occurred, if A happening affects B, is read as the probability of B given A, and is written with this line that we just read as given. So we're finding the probability of B, but what we're saying is A has occurred, and that's going to affect that probability of B. So in other words, they're not independent events. The calculation then is to take the probability of A and B right here, and then divide it by the probability that A has happened. So I'm going to move this over and just put this here. Whatever event is given is what goes in the denominator. So whatever event you put after that given line is what you're going to be dividing by. And this is a great formula. We're going to use it in a lot of our problems, but sometimes we're actually able to just use a table. If we're given our information in the table, we can kind of bypass the formula and just use the table in order to find the probability. So take a second here to kind of label the table that I have there the way that I have it labeled here. We're talking about tons of waste and like a garbage dump. We have a bunch of different types of materials here, and then we can split it into recycled and non-recycled with each of those types of material. So I've given each one of those things a letter just to make our notation a little bit easier. So paper is P, metal is M, so on and so forth. And we're going to use that in our notation as we're doing our problems. You'll notice down at the bottom here, I also found the totals for the recycled and non-recycled, and then I found the total overall amount of waste that we have here in the dump. So our first probability that we're going to find is the probability that a sample of non-recycled waste was plastic. So what we're given is that it's a sample of non-recycled waste. That's what we're given. So non-recycled, I'm using NR to notate that. And we want to find the probability that that was a piece of plastic. So I'm going to, what do I use for plastic over there? L. So that's what we're looking for, the probability that's plastic, given that you know it's a non-recycled piece of material. So the fact that we're given it's non-recycled tells us we really are only focusing on this column right here. So that limits our sample space. We're not going to put that 229 down in the denominator. We're going to put the 161.2 down in the denominator. And then this is where we kind of are bypassing the formula. You know, instead of calculating what the probability of A and B are, we don't need to do that. We know that the probability that it is both non-recycled and plastic is right here. Or that's the amount that it was. So we can just put that 24 up in the numerator. And then when we calculate that probability, 24 divided by 161.2, we get about 14.9% or 0.149. So one of the harder parts here is just figuring out what is given and what you're finding the probability of. So in the next one, it says the probability that a piece of selected plastic, I'm going to stop right there. So what we know is it is a piece of plastic. We want to find the probability that it's not recycled. So now we reverse that condition from the previous problem. So now we have limited our sample space to only be looking at the plastic material. So I'm going to get that total over there. It's pretty easy to find. It's 25.4. That's what's going to go in our denominator. And in the numerator, well, it's still that 24. And that's obviously going to be a pretty high percentage, 94.5%. Okay, our last example here in example 1, the probability that a piece of material was recycled metal. So this isn't a conditional probability. This is just asking for the probability that you have a recycled metal piece of material. So it's both recycled and metal. So recycled and metal is right there, 6.3. But this is out of all of the waste there. There was no condition given to us. So we're going to put the 229.1 down in the denominator. And this ends up being about 2.7%. So you got to know the difference between just finding an overall probability like this one and finding a conditional probability like those two were. All right, another table. This time we're just given the notation. So this is asking for the probability, and they already gave us the totals here. That's nice. These are actually called this here, just going to circle that. These are called the marginal distributions. For those of you taking AP stats someday, that might pop up. That when you're finding these totals here, you're really finding the marginal distributions. The distribution of, in this case, gender, and then the job type right here. So we're looking for the probability in the first one of selecting a full-time employee, given that you know they're a male employee. So you know it's a male employee, so you're only, again, when you're given a table, these are pretty easy, because now you're only focused on the males, because that's what is given. So your denominator, you already know, is going to be 28. How many full-time employees were males? 12. So 12 out of 28 is about, I'm going to do these in decimals. You do percents or decimals, so I'm just kind of changing it up to show that either way is fine. So the next one, now we're going to reverse that condition. Now we're given that they're a full-time employee. So now we're looking at just the full-time employees. And what's the probability that they're male? So we're still going to have that 12 up in the numerator. And this is about 0.3. All right. Actually, let's see. Exactly 0.3. So last one here, probability that they're female given that they're part-time. All right, part-time is our given. So we're looking right there. 31 is our denominator. How many females were part-time? 15. So then we're going to have about 0.484 here. So that's getting conditional probabilities from a table. All right, another useful tool in probability is using a tree diagram, and it's especially useful if you're dealing with conditional probabilities. So take a second to read through what we've got going on here. 28% chance of it being sunny outside. If it is not sunny, or in other words, if it's cloudy, there's a 31% chance of rain. And if it is sunny, there's a 4% chance of rain. We're going to make a tree diagram using these percentages, these probabilities. So we know that it's either going to be sunny or cloudy. So I'm going to give some variables to what's going on here. So I'm going to just say that being sunny is S. And then not being sunny or cloudy, I'm just going to call that C. And then we either have rain or we're not going to have rain. Okay, so I'm just going to write, I'm going to just put it up here. Okay, so what we start off with first in our tree diagram is the fact that it's either going to be sunny or cloudy. So I'm going to do that. Then I like to put the probabilities on the actual like branches of the tree diagram. So the probability of it being sunny is 28%. And they don't tell us this, but the probability of it being cloudy, since these are complements here, would be 0.72. So this you got to actually calculate. You got to know that as you make a tree diagram, that the branches themselves are complements with one another. So if it's sunny, it's either going to rain or it's not going to rain. If it's cloudy, it's either going to rain or not rain. So let's put on here first the probabilities that we were given. It says if it is cloudy, there's a 31% chance of rain. So I can put that right there. If it's sunny, there's a 4% chance of rain. So I can put that right there. Now remember, these are complements here. So if it's a 4% chance of rain if it's sunny, that means there's a 96% chance that it's not going to rain. And there's a 69% chance that it's not going to rain if it's cloudy. So those are the actual conditional probabilities right there. Just as an example, just grab one here. This represents the probability that's going to rain given that it was sunny. That might actually be a question that we have to answer later on. Actually, I think that is right here. That's C. I'll come down here and just put 0.04 right there. Okay, so let's now find our and probabilities. The probability that it is sunny and going to rain, this is kind of where the tree diagram is slick. You just multiply through your branches there. So the probability that it's going to be sunny and raining is going to be 0.28 times 0.04, which is going to be 0.0112. And then we'll continue to multiply through the tree diagram. So our next one is going to be those multiplied together. So that's going to be 0.269, and then 0.223, and then 0.497. Okay, I'd recommend, maybe just doing a couple of these multiplications and make sure that you're understanding where they're coming from. And I'm just going to clean this up and just write this as 0.0112. Just going to do a quick double check to make sure I got these numbers right. Now, if you do everything right, these are the only 4 things that could happen. So these should add to 1. Okay, those better add up to 1, which they do, because those are the only 4 things that can happen. Okay, so let's see what we got going on here. The probability that it is sunny and raining. Well, we found our and probabilities already. Okay, so this first one here, A, we're going to find right there. That is 0.0112. Okay, the probability that it is going to rain, well, that one's kind of tricky. I'm going to get rid of this now, because there's 2 scenarios where it rains. It's either going to rain if it's sunny or if it's going to rain if it's cloudy. Okay, we'll get over the fact that it's weird to have it raining if it's sunny, and that's why it's only a 1% chance. But it could be either of those things. So what we're going to do there, I'm going to even write that. So probably that it's raining and sunny, or the probability that it's raining or cloudy, and cloudy, sorry. So raining and sunny was 0.0112, or we're going to add those together, 0.223. So this is a total of 0.2342. All right, this last one here, it's actually backwards. The chance or the probability that it's sunny given that it rained, that's not in our tree diagram. This is called reversing the condition. You're going to need the formula for this one. So let's remember what the formula was. Probability of sunny given rain would be the probability that it's sunny and raining divided by, remember, this is important, whatever you're given is what goes down in the denominator. So the probability that it's raining. So the nice thing is we've calculated these things already. Sunny and raining, that was the first one that we calculated, 0.00112, or excuse me, 0.0112. And then the probability that it rains overall, that was part B, we found that to be 0.2342. So this is going to end up being 0.0478. All right, take a second to read through example 4 there. And once you do, you need to understand what's being asked so you can figure out which way the condition is going. It says, find the probability that a flight, I'm reading the final question here, find the probability that a flight departs on time also arrives on time. So what we're looking for is a probability that a flight departs on time, that a flight that departed on time, so we know that it departed on time. We want to know the probability that it also arrives on time. I wonder if I could have made this smaller. Arrives on time. Okay, that's what we're looking for. What's the probability that something arrives on time if we know that it departed on time? Well, the nice thing is they gave us these percentages. 80% of airlines' flights depart on schedule. That's what we want down here, 87%, or 0.87. 72% of its flights depart and arrive on schedule. That's what we want in the numerator, because that's your and. This is going to be 0.9. So 90% of flights that depart on time will arrive on time, obviously at a different airport. All right, in our last example here, take a second to read through it, and I'm going to start jotting down some of the probabilities that they give us. So we know that the probability of being male is 58%, and the probability of being male and that they jog is 0.2. Okay, I'm going to make a table here to help us answer this question. So we've got two variables going on here. The type of exercise, and that's either jogging or walking, and then gender, and that's either male or female. So here's what we know. I'm going to put everything that we know here in red since that's what I got going on. We know that is 58%. Overall, male is 58%. 20% of all the respondents are both male and joggers. So what we can do is now find the missing pieces here. Okay, we're assuming that male and female are complements, so this is going to be 0.42. And joggers are either male or female, so this is 0.8. Since we know that these two probabilities have to add up to that 58%, this has to be 0.38. All right, so here's what we're going to find here. Find the probability that a male respondent jogs. Okay, so in other words, we're told it's a male respondent. We want to know the probability that they jog. Okay, so it's not, the answer is not just the 0.2. That's if you were finding the probability of all the respondents. What's the probability that they were a male jogger? Well, we know that that's 0.2. We have that right there. We want to know the probability that if you know they're a male jogger, if you know they're a male, what's the probability that they jog? So using the table, this is where the table's nice, is we've limited our sample space. Remember, what you're given goes in the denominator. And then the and goes in the numerator. So this is going to be about 34.5%. And then I just have this little blurb down here. Just notice the difference between these things. The probability the respondent is a male who jogs is of all respondents, male and jog, that's 20%. That was given to us. But the probability that a male respondent is a jogger is the probability that you know that they're a male respondent, and you're finding the probability that they jog. That's what we just found. That's 34.5%.